Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. Today we are going to be discussing about transition metal cyclobutadiene complexes, their reactivity. We are going to look at another very interesting ligand which probably constitutes the bulk body of organometallic literature. I mean, this is specifically about transition metal cyclopentadienyl complexes. So, for us, if we look at how this lecture is progressing, we have started with allyl systems, which are 3 carbon systems, then moved on to look at butadiene systems, which are 4 carbon systems, and then we have proceeded further to look at cyclobutadiene system, which is also a 4 carbon but cyclic system, and this had been the focus of our talk in the last 2 or 3 lectures, and then we will try to wrap that up in today's lecture and then move on to metal cyclopentadiene, which is a 5 carbon system subsequently. So, with this let me just talk about the reactivity of these metal cyclobutadienyl complexes. Now, before we have to look at the reactivity of these complexes, one needs to understand the metal ligand interaction for these complexes. In our past lecture, I have sort of given a brief comparative perspective of how cyclobutadiene molecular orbitals compare with regard to butadiene as well as with regard to allyl systems, and today we are going to look at it in bit more depth about which all metal orbitals interact with what all ligand orbitals of cyclobutane ring. With regard to cyclobutane ring, I must mention that I had spoken about their structure, the degeneracy of various molecular orbital as a result of its square structure as opposed to its rectangular structure, in which these two side 2 and side 3 orbitals which were degenerate would lose their degeneracy, and then in that case we would be having 4 different molecular orbitals, psi 1 all the way to psi 4, as was observed in butadiene system. So, structure of bonding. Of cyclobutadiene. So, the ligand would have, as discussed earlier, 4 p orbitals So, the first one is psi 1, which is a bonding orbital. So, this is the ligand orbital, and the metal orbital that interacts with the psi 1 ligand orbital are mainly the s orbital of the metal or the metal pz orbital and the metal dz square orbital. So, these interaction of psi 1 with the metal orbitals are primarily of sigma type, that these are sigma interaction. Now, sigma interaction is an interaction whereby at the internuclear distance of the interacting atom, in this case the ligand and the metal, the electron density should be the highest or maximum. Now, if you look at the overlap that would occur between an s orbital and this bottom face of the ligand orbital, you would see that they would form a sigma bond, and by the definition that maximum electron density resides in the internuclear axis between the ligand and the metal interacting atoms. And the same sigma bond can also be seen forming with pz orbitals or dz square orbitals, all moving up from the bottom face of this psi 1 ligand orbital. The next orbital for cyclobutadiene is a psi 2 orbital, and this is psi 2, and similarly one can write psi 3 as so these two shown in black are the degenerate orbitals that results the square structure of cyclobutadiene ring. This provides the diradical character of cyclobutadiene, and they interact with metal orbitals, for example psi 2 interacting with py and psi 3 interacting with px. Now, the orientations of this pi and py are such that they form pi type overlap with the metal orbitals, and corresponding the d orbitals that interact with psi 2 are d yz and dxz. So, these are metal orbitals which sort of interact or which interact with the psi 2 and psi 3 of the cyclobutadiene ligand. The metal orbitals can arise from p orbitals, py for psi 2 and px for psi 3, as well as d orbitals like dyz for psi 2 and dxz for psi 3. Now, these interactions is of pi type in the sense that if this orbital were to interact with this, so this lobe will interact with that and this lobe will interact with this. So, between the nuclear distance of the interacting atoms, there would be no residual electron density, but it will be above and below the plane of the containing the interacting internuclear axis. So, this interaction is a pi type. One can conceive along the same line d orbital interacting with psi 2, where this lobe will interact with that and this lobe will interact with that. Again, such an interaction is pi type interaction. Now, as side 2 and side 3 are degenerate, they are complementary to each other, and similarly one can envision likewise kind of interaction pi type when this lobes interact with that, and this will be for the p x orbital, and likewise for the orbitals, these two orbitals will interact with these two orbitals for the dxz. Now, the last is an antibonding orbital. This is sigma, then two degenerate pi orbitals, that both the degenerate pi orbitals are shown in the black, and the last set of orbital is an antibonding orbital. And so this is termed as psi 4, and this interacts with dx square y square orbitals. Okay, this is dx square y square orbital, and this interaction is kind of one of its kind, and these are called a delta type of interaction, where the whole of the dx square y square orbitals interact sidewise with the bottom face of psi 4. Now, this diagram clearly presents to you how the cyclobutadiene orbital interacts with different metal orbitals. Now, apart from the various kind of interactions like the sigma interaction, 2 pi type interaction and 1 delta type interaction, one can also see that the strength of the interaction obviously would vary. For example, a sigma interaction would be the most stronger one, followed by pi type interaction, and among all these 4 interactions, delta is the weakest kind of interaction one can envision. So, these diagram provides a brief overview of how cyclobutadiene moiety interacts with various kinds of metal based orbitals, and it also sort of gives you the feeling why after interaction of cyclobutadiene with the metal center, they show square geometry, whereas in free cyclobutadiene is a rectangular structure. So, free cyclobutadiene is rectangular, whereas transition metal cyclobutadiene is square, and this diagram explicitly explains the reason for such difference in structure before and after binding to transition metal complex. As mentioned in the earlier discussion, that transition cyclobutadiene attains aromaticity by binding to transition metal, because it goes from a radical neutral state to a dianionic aromatic state containing 6 pi electron as a result of electron donation from the metal. Now, having attained aromatic structure, the cyclobutadiene ligand also behaves like an aromatic compound. For example, it can go exhibit electrophilic substitution reaction similar to that observed in any other aromatic compounds, for example, in benzene. So, now we are going to look at some interesting reactions exhibited by transition metal cyclobutadiene complexes as a part of their reactivity study. So, like aromatic compounds, it undergoes electrophilic substitution reactions. For example, the reaction of this half sandwich compound, cyclobutadiene, iron, with CH3COCl in presence of AlCl3, like any standard acylation reaction. The eta 4 bound cyclobutadiene converts to eta 3 bound allylic ligand, similar to one shown over here, and the electrophilic substitution occurs at the ring. Needless to say that both of these are 18 electron compounds. For example, 4 from cyclobutadiene, then 8, to overall making 12, and 6 electrons from 3 COs. So, 12 plus 6, 18. This is the 18 valence electron compound, and upon reaction with acetyl chloride, this eta 4 bound cyclobutadiene ligand transforms to eta 3 bound allyl ligand, and here too the complex becomes 3 from the ligand, 8 from the metal, so and 6. So, this is 17 electron with a cationic charge. So, overall it becomes a 16 valence electron compound, which sort of is not too stable, loses back its proton to give the acylated cyclobutadiene compound bound to iron tricarbonyl. So, now this again attains the 18 valence electron compound structures. So, what we see that similar to what normal aromatic compounds exhibit, that they undergo electrophilic substitution reaction. Here also we saw that this hydrogen of one of the hydrogen of the ring hydrogens of cyclobutadiene can be made to substitute with acetyl chloride, giving CH3CO bound cyclobutadiene ring, and that reaction is very much similar to what is observed for aromatic electrophilic substitution reaction. In the process, the hapticity of cyclobutadiene changes from eta 4 or in the reactant to eta 3 allyl type in an intermediate compound back to eta 4 in the substituted acylated cyclobutadiene ring, and As far as the total valence electron of the complex is concerned, it goes from 18 valence electron to 16 valence electron in this cationic compound to back to 18 valence electron in the acylated cyclobutadiene ring compound. Cyclobutadiene ring having CH2X substituents are very easy to solvolyze or readily undergoes solvolysis, and here is an example. Cyclobutadiene CH2Cl with Fe CO3 in presence of SbCl5, a halide abstraction occurs resulting in elimination of SbCl6 minus and generation of this compound, which is cyclobutadiene CH2 plus Fe CO3. Now, this charge CH2 plus charge as adjacent to the cyclobutadiene ring is resonance stabilized, resulting in an exocyclic double bond and eta 3 allyl compound, where the net positive charge is now delocalized in the ring, bound to Fe CO3 compound, and that then reacts with OH minus, giving this CH2 OH Fe CO3 compound. So, this is the interesting reaction where we saw that CH2 halide moiety on the substituents on the cyclobutadiene ring is prone to solvolysis, and the reason is because of the stabilization of the charge that is generated upon the leaving of the halide group and subsequent attack of the OH minus results in the formation of the alcohol. Likewise, one can go reverse by having a proton which will protonate this alcohol, and then eliminating water, one can also generate this cyclobutadienyl stabilized cation, which can then further undergo solvolysis reaction. Another very important aspect of cyclobutadiene transition metal compound is the fact that they are source of free butadiene for various organic transformations. For example, C4H4 FeCO3 is a source of free cyclobutadiene. In organic synthesis. So, this I will explain with an extremely intriguing source of reactions, which will show that they can be effectively used for synthesizing many different kind of organic compounds, where C4 cyclobutadiene FeCO3 is a source for free cyclobutadiene. For example, the compound C4H4CO FeCO3 in presence of an oxidant cerium-4 produces cyclobutadiene. Okay. Now, please note the structure which is written over here is of free cyclo free cyclobutadiene and hence rectangular, whereas this one is symmetrical and bound to aromatic and hence square. So, upon decomplexation, cyclobutene ring changes from square geometry to a rectangular geometry, which can react with acetylene, terminal acetylenes, giving these divar benzene compounds. So, this is just 2 plus 2 cycloaddition of one of these double bond with that of the olefinic ring, resulting in these divar benzene compounds. It can also react with quinones to give this cycloaddition product. So, here one of these undergoes 2 plus 2 cycloaddition with the quinone, which in presence of light and further undergo 2 plus 2 cycloaddition reaction, leading to the formation of a cubic compound of the type this, that in presence of KOH, water gives this compound of cubic structure, and that in presence of T butyl per esters and thermolysis gives decarboxylates and gives this perfect cubanes. And also this free cyclobutadiene at temperature is kind of unstable at 35 degree Kelvin, undergoes reaction to give this so this is undergoes dimerization. So, as if 2 of the cyclobutadiene unit, 2 of these unit dimerizes to give this compound. So, we have 2 of these cyclobutadiene with 2 double bonds in the end. So, what this provides is a rich chemistry that transition metal cyclobutadiene complex can give, that can give rise to plethora of compounds very difficult to synthesize otherwise, and that can all arise from the simple precursor of cyclobutadiene iron tricarbonyl. So, with that I will conclude today's lecture. Hopefully, I think you will go home with appreciation for various kinds of different and intriguing chemistry exhibited by cyclobutadiene iron tricarbonyl compounds, as well as other cyclobutadiene transition metal compounds, and with that we conclude our discussion on cyclobutadiene complex, and then we will take it up further in the next class, where not only will just look little bit more up on these cyclobutadiene transition metal complexes, but also on cyclopentadienyl complexes, which form substantial body of literature in transition metal organometallic chemistry. So with that, thank you, and I look forward to being with you in the next lecture.